In this video, we will be predicting the molecular geometry of molecules with lone pairs. For a quick refresher on the general theory of molecular geometry, check out the video titled Predicting Molecular Geometry Theory. The link will be in the description below. In general, when it comes to predicting molecular geometry, we use VSEPR theory. VSEPR theory is spelled V-S-E-P-R. Which stands for valence shell electron pair repulsion theory. Generally speaking, when atoms bond to form molecules, only the electrons in the valence shells of the atoms are involved in the formation of the bond. The electrons in the inner shells do not participate in the covalent bonds. VSEPR theory takes into account electron pairs, hence the name valence shell electron pair repulsion theory. In an atom bonded to other atoms in a molecule, there are two types of electron pairs taken into account. There are lone pairs and there are bonding pairs. Lone pairs are pairs of electrons that do not participate in covalent bonds and are not shared, hence the name lone pair. They are all alone by themselves. In the previous videos, we talked about predicting molecular geometry of molecules without lone pairs. In this video, we will take lone pairs into consideration. Coming back to VSEPR theory, electron pairs have a tendency to repel each other, since like charges repel, whereas opposite charges attract. So for instance, if we have two negative charges, they will tend to repel each other, right? They want to move away from each other. Likewise, if we have two positive charges, they will also tend to repel each other. Whereas on the other hand, if we have a positive and a negative charge, right, two unlike charges, they will tend to want to attract each other. Due to this, electron pairs want to stay as far away from other electron pairs as possible. They want to maximize the distances between themselves. So this is what gives molecules their geometry or their shape, right? It's because electron pairs don't really like each other and they want to stay as far away from each other as possible. However, the difference between bonding pairs and lone pairs is that covalent bonds are bonds shared between two atoms, right? So therefore, the pair of electrons in a covalent bond or in a bonding pair are attracted to the nuclei of both atoms and vice versa. For example, let's say we have one nucleus right here and then another nucleus over here, and then in between the two nuclei we have a pair of electrons, right? And this pair of electrons is going to be the covalent bond that bonds these two atoms together, right? So on the one hand, the nucleus will be attracted to the pair of electrons, while on the other hand, the pair of electrons will be attracted to the nucleus or the nuclei, right? So if we draw a covalent bond like we just drew, we see that there are attractive forces holding the atoms together, and that's what a bond is, right? Electrons in a covalent bond are tightly held by attractive forces of the nuclei. Think of it as being stuck or, quote unquote, bonded together. Because of this, they can't really move freely because they are being held back by the pull of the positively charged nuclei. So they can't travel very far away. On the other hand, lone pairs that are not held by the attractive forces of both nuclei, but rather just the nucleus of the atom it's attracted to, it has more freedom than the bonding pairs because it's less tightly held. So let's say we have a pair of electrons over here by themselves. They will be more able to freely move about without being held back by the pull of the nuclei. It can travel farther away, and therefore it takes up more space, right? And because it takes up more space, they can come into contact with the surrounding electrons more often, and therefore experience greater forces of repulsion. So now I want to talk about two similar but distinct concepts that are often misunderstood. Electron pair arrangement and molecular geometry. So up until now, the terms have been used somewhat interchangeably when dealing with the molecules without lone pairs. But now we will differentiate between the two. Right, so molecular geometry is how the atoms are arranged around the central atom, whereas electron pair arrangement is how the electron pairs are arranged around the central atom. So let's look at these two terms. Right, we have electron pair arrangement, and this deals with the electrons, whereas the molecular geometry, the geometry deals with the atoms themselves, right? And so if there are no lone pairs around the central atom, the electron pair arrangement and the geometry will be identical because each pair of electrons is attached to an atom. However, the electron pairs however the electron pairs are arranged, so will the atoms. Because lone pairs are not attached to atoms and exert greater repulsive forces than bonding pairs, they will affect the geometry to a greater extent. So for the following examples, we will deal with molecules that have only trigonoplanar and tetrahedral electron pair arrangements. So molecules that have up to 4 electron pairs, bonding and lone pairs included. We will also be using the notation ABX, EY, right? Which is similar to the previous notation, the difference being that E stands for a lone pair on A, the central atom, and the Y subscript stands for how many electron pairs there are. So E means that there's 1 lone pair on the central atom. E2 stands for there being 2 lone pairs, etc. And again, B sub X is the number of atoms surrounding A. So let's just go ahead and make a chart. So let's say we have ABX, E sub Y. A is going to be the central atom. B is going to be the surrounding atom. Right, and then E is going to be the lone pair. And then X is going to be the number of the surrounding atoms, right? 1, 2, 3, or 4, etc. And then Y is going to be the number of lone pairs. So Let's start with a simple molecule with the notation AB2E. Right, so down here we have AB2E. And this means that this is a molecule where the central atom has two atoms surrounding it and one electron pair surrounding it. For example, sulfur dioxide, which is SO2. As always, let's draw the Lewis structure first. Sulfur is in group 6, and oxygen is also in group 6. So therefore, there's going to be 6 valence electrons on the sulfur and on each of the oxygens as well. So in total, we have 6 plus 6 plus 6, which is going to be 18, right? 6 for the sulfur and then 6 for each of the oxygens, giving us a total of 18 valence electrons to account for in total. And so now to draw our Lewis structure, starting with the central atom, the sulfur, we draw its Lewis structure first. So we have sulfur, which has 6 valence electrons surrounding it. And then we attach our oxygens to our sulfur using covalent bonds, or a sharing of 2 electrons. Right, so now we attach our oxygens, one to each of the free electrons next to the sulfur. And then one more oxygen over here. However, we want each atom in the molecule to have an octet, which is 8 valence electrons surrounding it. So we share any unpaired electrons using a double or triple bond. So we take one of the unpaired oxygen electrons and pair it with one of the lone sulfur electrons to form a double bond. And since we can't form another double bond with the other oxygen, since sulfur can't have more than 8 electrons, we move another one of the sulfur electrons over to the other oxygen. So now we have a Lewis structure that looks something like this. Right, we take our sulfur atom in the middle, we take one of our lone oxygen atoms, and then we form a double bond with the sulfur. Right, so we have something like this. And then for the other oxygen, we take one of the sulfur electrons, and then we complete the other oxygen's octet. So one of these sulfur electrons, we form a double bond with one of the oxygen lone electrons, and then the other sulfur electron, we use it to complete the other oxygen's octet. So now we have a Lewis structure that looks something along the lines of this. A double bond, sulfur, a lone pair, and then one oxygen. Right, so here's our final Lewis structure. So finally, so now we might say that the geometry of sulfur dioxide is trigonoplanar, since there are 3 electron pairs around the central sulfur atom, and a planar geometry would maximize the distance between the electron pairs. But the presence of the lone pair causes the bonding pairs to orient themselves such that they bend away from the lone pair. So the geometry of SO2 will look something more like this. We have our sulfur in the center, right? And the bonding pairs will orient themselves away from the lone pair on the sulfur. Right, because the steric number of sulfur is 3, right? Steric number is going to be equal to the number of pi bonds plus the number of lone pairs. Right, so since the steric number of sulfur is 3, the electron pair arrangement is still trigonoplanar. However, the geometry, right, the arrangement of the atoms themselves is going to be bent, right? Think of taking a straight piece of wire and then bending it. Normally, the distance between the electron pairs would be 120 degrees. However, since the lone pair exerts a greater force of repulsion than the bonding pairs in each of the sulfur-oxygen bonds, it pushes them further away from itself and therefore closer together. So the angle between the two oxygens is less than 120 degrees. Right, and so that's going to do it for the geometry of molecules with the form of AB sub 2 E. So for our next example, we have molecules in the form of AB3E, right? So A, B sub 3E, right? And that's going to be a central atom with 3 atoms surrounding it with a 1 lone pair. For instance, an atom like ammonia, which has the formula of NH3. So first, let's draw our Lewis structure, right? So nitrogen is in group 5, so it has 5 valence electrons. Hydrogen, on the other hand, is in group 1, so it has 1 valence electron on each hydrogen. So 5 plus 1 times 3 is equal to 8 valence electrons. So first we take our central atom, nitrogen, right, and then we draw its Lewis structure. So 1, 2, 3, 4, 5 valence electrons. And then we add our hydrogens to the unpaired electrons on nitrogen, right, like so. So 1 hydrogen, 2 hydrogen, and then our 3rd hydrogen over here. So if we count up all of our electrons, we have a total of 8, which matches our the total we calculated earlier. And so finally we can replace the bonding pairs with bond lines if you want. So our new Lewis structure might look something like this. Right, and now since the steric number of nitrogen is 4, right, because like we said before, the steric number is equal to the number of sigma bonds plus the number of lone pairs. So since we have 4 sigma bonds and 1 lone pair, 3 sigma bonds and 1 lone pair, the steric number is going to be 3 plus 1 equals 4. Right, so since our steric number is 4, the electron pair arrangement is going to be tetrahedral. Right, and so since our electron pair arrangement is tetrahedral, our ammonia molecule is going to look something closer to this. We have our nitrogen in the center. Right, here's our lone pair. Here's 1 hydrogen bond. Here's another hydrogen bond that's coming out of the page. And 1 more hydrogen bond going into the page. Right, so now we have a tetrahedral molecule. However, the presence of the lone pair at the very top causes the nitrogen hydrogen bonds to be pushed further away from itself and therefore pushed closer together, right, closer to each other. So instead of the angles being 100 and 109.5 as they are, as they would normally be in a tetrahedral molecular geometry, the angles between the bonds is slightly less than that, so around 107.3 degrees. And so we call this geometry trigonal pyramidal, right? Trigonal pyramidal. Right, this is going to be the geometry. Even though the electron pair arrangement is still tetrahedral, the geometry is going to be trigonal pyramidal. The 3 hydrogens form a triangle, or the base of a pyramid, and the nitrogen is the apex, or the top of the pyramid, hence the name trigonal pyramidal. Remember, geometry deals with the atomic arrangement, not the electron pair arrangement. So it's like the lone pair is going to be invisible. And so for our final example, we have molecules in the form of AB sub 2, E2. A, B sub 2, E2. And that is molecules with 2 atoms and 2 lone pairs around the central atom. So a compound like water, which is H2O, will fit this description. So starting with the Lewis structure, oxygen is in group 6 and hydrogen is in group 1. So we have 6 plus 2 times 1, which is going to be 8 valence electrons in total. And so starting with the central atom, oxygen, we draw the Lewis structure, which is just going to be oxygen with 6 valence electrons surrounding it. And then we add our 2 hydrogens to the unpaired valence electrons, right? So we draw 1 covalent bond, and then we draw another covalent bond. So here's the Lewis structure of water. As you can see, we have a total of 8 valence electrons like we originally accounted for. So now, since there are 2 bonding pairs, right, 2 pi bonds around the central atom, the oxygen, right? Because all single bonds are sigma bonds. So since we have two bonding pairs and two lone pairs, the steric number is 2 plus 2, which is 4. Right, so therefore we have a tetrahedral electron pair configuration. Right, so if we were to draw this in three-dimensional space, our molecule will look something like this. Here's our oxygen atom in the center. So we have one lone pair up here, one lone pair over here, one hydrogen bond coming out of the page, and then another hydrogen bond going into the page. Right, tetrahedral. So this is going to be the electron pair configuration. And similar to ammonia, the lone pairs will push the OH bonds closer together, right? So these two bonds, it will push these two bonds closer to each other. However, the lone pair at the top will push the bonding pairs away from itself and therefore push them downwards and closer together, whereas the lone pair on the right will push the bonding pairs away as well, right? It will push them to the left as well, and therefore push them even closer together than before. So it will have a bent geometry, just like sulfur dioxide. But the extra lone pair will cause it to be even more bent, right? The angle between the OH bonds would be around 104.5 degrees. And so that's going to do it for this video. Hopefully you learned something. With that being said, thank you for watching and have a great day.